Now that we've introduced the dot product, let's come back to the problem we started with. So we have a vector u and a vector v, and we decided the vector, we were looking for a vector that's in the direction of v and with length of u times cosine of the angle theta between them. So that works out to be length u cosine theta, that's the length, and then the direction vector of v is v over length of v. Now we can rewrite this. So the length u cosine theta is u dot v over length of v. So we get that this is u dot v over length v times v over length v, which we can then rewrite again. The denominator is length v squared, which is v dot v. So we can rewrite it as u dot v over v dot v times the vector v. So just a few different ways of writing this. The point being that now the dot product is something that we know how to calculate. So in any case, we call that vector that we get the projection of u onto v, and we'll write it as proj sub v of u. And the coefficient of v, which is length u cos theta, or u dot v over length v, this we call the scalar component of u along v. We do need to be a little bit careful. The picture I drew assumed the angle between u and v was acute. But if it was an obtuse angle, like we could also have used this vector is still parallel to the incline, then cosine theta would be negative. So this expression for the length would be negative, which doesn't make sense. But you can check that the signs work out so that this formula for proj is actually still correct for any angle. But instead of showing that, I want to show another more algebraic way of coming up with this formula for proj vu, which will also show that this formula is correct. So the vector proj sub v of u has the following properties. First, it is parallel to the vector v. And secondly, if I break up u as proj sub vu plus some other vector, call that other vector w, then the leftover piece is orthogonal to v. So now I claim that these two properties uniquely determine proj vu. So that formula is forced on us just by these two properties. So first, property 1 tells us that proj vu, if it's parallel to v, then it's equal to av for some real number a. So we just need to figure out what a is. Now, the second property, so we write u is equal to proj vu plus w, which is just av plus w. Now I'm going to dot both sides with v, so u dot v is equal to av plus w dot v. But now by the distributive property of the dot product, that's av dot v plus w dot v. But since we said that w is orthogonal to v, this term cancels out. So we get u dot v is equal to a v dot v. So we solve, we get that a, coefficient a is u dot v over v dot v, and so proj sub v of u is u dot v over v dot v of v, or times v. So that's another way of seeing this formula. So for example, let's say we're asked to find the projection of u equals 1, 0, negative 1 onto v equals negative 1, 3, negative 2. So our formula is proj vu is u dot v over v dot v times v. So u dot v will be negative 1 plus 0 plus 2 is 1, and v dot v will be 1 plus 9 plus 4 is equal to 14. So we get that the projection of u onto v is 1 over 14 times v, which we could leave like that, or we could write explicitly this is negative 1 over 14, 3 over 14, negative 2 over 14. One important application of the dot product is the concept of work in physics. So recall that work is defined as force times distance. However, if the force being applied isn't parallel to the displacement, for instance, you're towing a box along the floor, so the motion is horizontal, but you're holding it by a cord, so the force being applied is diagonal, then the relevant work will just be the distance times only the component of the force that's in that direction. So the scalar component of F along the distance or the displacement vector, so that becomes F dot product D. Again, so D is the displacement vector. So let me summarize. The work done by a vector force F through a displacement vector D is the dot product F dot D. So here, F is still a constant force. Later in the course, we'll be able to generalize this further to a moving force that's changing direction.